Going live. And we are live.
Hello, everyone. Welcome to the audio Programmer Virtual Meetup. My name is Timur. We are here with the 7th edition of the Audio Programmer Meetup, the September edition. How do we get to September? It's September already. Wow. So yeah, thank you so much for tuning in. It's a pleasure to be here as always. As you might see, I have bookshelves behind me again, which means I'm back at home in London in the UK. If some of you have tuned in last time, you remember that last time I was in Greece and I had a power outage in the middle of the meetup. So I'm pretty sure this is not going to happen tonight. Yeah, so thank you very much for being here. We have, again, wonderful guests. Obviously, we have my co-host, Josh. Hello, Josh.
Hey, how's it
And
going?
then we have 3 guests for you. Today we have Matt Phillips, who is a DSP and software engineer at Trident Audio. We have Spencer Salazar, who is a CTO at Output. And we have Celine Dedai, who is a diversity and inclusion consultant and also a job and career coach. Welcome, everyone. Do you want to just quickly introduce yourselves? And
Sure.
say hi.
Yeah.
Okay, I'll jump in first if you like. So my name is Matt Phillips. I'm a DSP and software engineer, currently working with Trident Audio, and also do some independent work on other projects. And I will be talking to you about non-linear DSP.
Great. Thank you, Matthew. Spencer?
Hello, everyone. Thank you, Timur and Josh, for having me on here. Really excited to talk about my thesis project called Orglyph. It's a sort of modular sketching environment for music creation. Really excited to show that. I'm also the CTO of a company called Output. We make music software for producers, musicians, film composers, and people like that.
Great. Celine?
Yeah. So yeah, I'm Celine. I used to work for Ableton. I've been working there for a while, and also for Thomann shortly. And nowadays I'm freelancing, and I will have a surprise for you because we are talking about ADC a bit today.
Yeah, exciting. And I'm Josh, and I'm the founder of the Audio Programmer. And I will also be speaking today about an introduction to the JUCE DSP module. And so before we get started, just a few quick announcements. As always, we would like to thank our sponsors, JUCE, Sonux, and Focusrite, for supporting the Audio Programmer Meetup. And also, for anybody that wants to continue the discussion after this meetup, be sure to join us on the audioprogrammer.com/community. So that's our Discord group. As Celine had mentioned before, we are also involved in ADC, Timur, Celine, and myself. And Celine is going to be talking a little bit more about ADC and some of the important announcements. So ADC is happening on the 18th and 19th of November this year in virtual form, and Celine will tell you more. Take it away, Celine.
All right, thank you. So yeah, I hope you all know that ADC is happening. And so this year, it's the three of the people that you see on the screen who are the actual team. So this is a big change compared to the previous ADCs. And this is also on purpose that the team is different because we want this ADC to be different. But before I come to that, I would like to maybe remind people that you can still submit a talk, and we would be absolutely delighted to see your submissions before Monday, before midnight on Monday, UTC, which is 1 a.m. London time, Tuesday morning. So check the website out if you're not sure, but please submit your talk, especially if you've never submitted a talk before, if you don't feel like you're part of the mainstream. So we really encourage minorities and people who have never submitted a talk to do it, because we want this ADC to be as colorful as possible. So there's that, but now about what's new about ADC. So a number of things are different. Well, it's a virtual conference, which is not really a decision, but this is a very nice thing because it allows me probably more people to actually join. It's going to be just from where you're sitting in front of your computer or standing, whatever. So I hope that more people can join, and maybe all of you. Also because the pricing structure has changed, so it's way more affordable this year. So please check it out. Also, this is the very first time that we have a dedicated code of conduct team for ADC, and part of my job, for instance, will be to provide guidelines for speakers, ensuring that ADC this year is most welcoming and that we are enabling open communication. What's also new is the proposal review process. Now the proposals are reviewed by the community, and the proposals are anonymized to mitigate bias as much as possible. Another good thing, which is not new, but nice for you to know, all presentations will be available for free after the conference anyway. But it would be great to see you at the virtual table. We use a tool called Remo. I don't know if you've been to an online conference. A number of online conferences have been run via Remo, and it kind of reproduces a bit the feel of being able to mingle with people because you're actually virtually sitting at a table. So that's really cool. What else I wanted to do? Yeah, code of conduct team. We would love to have more people on the team. The job is basically to make sure that if there is something that is happening related to communication or tension between attendees related to the code of conduct, that's the team that's gonna help with emotional support or taking action, talking to a speaker with a weird slide, or talking, maybe moderating chats with weird jokes that make some people feel uncomfortable and unwelcome. So I would love to see more people on the team, and perk is that you're gonna work with me. That's pretty awesome, maybe, I don't know. Anyway, so please come to us if you're interested. I'm happy to have a chat with you and explain to you what the actual job really is and what it means and how to get there. And yes, and about the sponsors for ADC, I think Josh is the best person to take over from there.
Yes. So if you're interested in sponsoring ADC, of course, with a condensed conference, we still need support to actually be able to finance this. And this is something that's a benefit for the audio programmer community at large. So if you're interested in sponsoring, please contact me directly at josh@theaudioprogrammer.com. So that's josh@theaudioprogrammer.com. And another thing is just want to give a link really quick to the actual submission for the conference talks. So you can actually find that on audio.dev, audio.dev. So that's the place where you go to where you can actually find out more about the conference and how to submit a talk and what the conference is all about. And I think that's everything that we have. So actually Celine just reminded me nicely that to actually submit a talk, it's audio.dev /submit-a-talk. So that's how you actually submit a talk. So I think we're ready to jump into our first talk. And who do we have, Timur, for our first talk?
Yeah, so thank you for the ADC announcement. I'm really excited to work on ADC with you all. Before we get to the first speaker, I actually would like to ask you a little favor. Please ask questions in the YouTube chat. And when you do so, please prefix them with the word question in capitals, because that makes it much easier for us to spot the questions. With that being said, yeah, I think we're ready for our first talk. So we have Matt Phillips. DSP and software engineer at Trident Audio, and Matt is going to be talking to us about a brief introduction to nonlinear audio DSP, which sounds really, really interesting. So I'm really looking forward to that. Over to you, Matt.
Okay, thank you so much. I'm going to share my screen. Okay, so really excited to be here. It's pretty excited when Josh said he wanted me to come and give a talk. And he, you know, I like a challenge. And so when he said, can you talk about nonlinear DSP in 30 minutes? I thought, sure, let's give it a whirl. There's a lot of information here. Those of you who have worked with nonlinear DSP before, you might be a little disappointed. It's probably not as in-depth as you might be used to. And those who've never worked with nonlinear audio DSP before, it may be a little complex in part. So I've tried to keep it pretty high level. But the purpose here really is to share some of the techniques that I've used in plugin development and really introduce the topic of nonlinear DSP and show you some of the tools that are available. So just a little bit about me. I've been working in the audio industry for over 15 years now. I've worked in fields of acoustical engineering, real-time DSP, hardware DSP design, software engineering. And this year at NAMM 2020, I released my first commercial plugins with Trident Audio. And had some nice reviews in the magazines that I've got on show there. So currently I'm working on more plugins and some other exciting projects that will appear over time. So just a quick overview of what we're going to be covering today. We're going to look at the term nonlinear systems, nonlinear DSP, and kind of cover what it actually means and what it means for us in audio world. A little section on nonlinear being a new buzzword in marketing and plugins, and just dispelling a few myths there. I'm going to talk about how to approach nonlinear audio problems. And then we're going to jump into a demonstration. I'll be doing I'll be running a Matlab session live because it's more exciting when things don't work. But we'll be looking at how you can use something called fuzzy logic to work with nonlinear problems. And then wrapping up at the end with just some guidance on how you can get started and some resources that are available to you. So we'll start with just a definition of what we mean when we say nonlinear. And at a system level, a system is nonlinear when the change in output is not proportional to the change in input. So the opposite to a linear system. And just to dive into that a little further, so unlike linear systems, nonlinear problems cannot be solved through what's called the superposition principle, which we'll go into a little bit more. So main thing to keep in mind there is the change in output not being proportional to the change in input. And when I say the superposition principle, what we mean there is for all linear systems, the net response caused by two or more stimuli is the sum of responses resulting from each individual stimulus, which is a little bit wordy, but what essentially that's saying is in a linear system, if input A is producing response X and input B is producing response Y, then A plus B produces response X plus Y. And that's how you can look at linear systems, and that will always be the case. That is not the case with a nonlinear system, which obviously raises some complications and extra work that we need to do in order to work with those kinds of systems. So in audio land, examples of components or systems that exhibit what I call well-known nonlinear behavior that we might all be familiar with as programmers and audio engineers. So things like tubes or valves, depending on where you're from in the world, transformers, magnetic tape effects, mechanical reverberation. So all these systems, these audio models based on these kind of systems are are kind of famous for their nonlinear behavior. So it's very difficult to approach them as a linear system because there are so many variables and parameters that aren't proportional. And in fact, something to keep in mind is that when we're modeling something, when we're working with something, any analog audio circuit exhibits degrees of nonlinear behavior. Some are, let's say, more nonlinear than others, but really any kind of analog electrical design is going to exhibit degrees of nonlinear behavior. And it's just a case of us choosing how we approach that, the scope of the project. So in DSP, linear implementations are often used to approximate nonlinear behavior, which is a completely valid way of approaching a problem. But in some cases, a linear representation is not an adequate solution for what we're trying to do. And the classic example, the example that I run into developing plugins, is that the sonic character of a vintage analog audio piece of hardware, for example, is often a result of its inherent nonlinearity. So if you try to represent that system using linear methods, then you're in fact glancing over some of the inherent characteristics and quality of that piece of gear. Just while we're kind of talking about plugins and nonlinear and audio DSP, nonlinear has become a kind of a buzzword in the audio software market. I'd say particularly regarding plugins, due to a combination of just marketing terms and just general information as it's spread around as people try to understand what nonlinear means. I've got a great example here from which I grabbed in December of 2019 from I call it an infamous gear discussion platform, make of that what you will, where someone had quite innocently said regarding a commercial plugin, love this plugin, it sounds sick as, will definitely end up buying when a nonlinear version comes out. And to my knowledge, there was, well, there was no penned nonlinear version of this specific thing, and it may already be nonlinear. But during discussions, people kind of say, well, if it's not nonlinear, then it's not going to sound as good as a linear design. So there's a little bit of misinformation out there. But the main thing really to keep in mind is that nonlinear signal processing is used to address complex problems that cannot be approximated by linear methods or cannot be linearized in an acceptable way. So nonlinear signal processing is by no means a must-have for every audio application. So if you can solve a problem through linear methods and it sounds great and you've achieved what you want to, that's completely valid. And in fact, nonlinear is really something that you delve into for specific problems. And modeling vintage or analog gear is one of those instances. But just something I wanted to throw out there, and certainly you see references to nonlinear more and more in forums and marketing and chat rooms and that kind of thing. So regarding approaching nonlinear audio problems, and for example, we're going to use modeling an existing hardware device. These are the steps that I personally take when approaching a problem like this. It's not necessarily the way that these problems have to be approached. I'm just sharing with you my approach and how I do things, and hopefully that might give you some ideas or just give you an insight into how I tackle these particular problems. And when I have a new piece of audio gear, particularly if it's vintage audio gear with pedigree and a well-established piece of equipment, the temptation is always to rush in and start looking at schematics and start running signals through it, taking measurements, however you choose to do that. What I always like to do is take a step back and spend a lot of time using the device without thinking about how I'm going to approach it, how I'm going to model it. Just use the device, learn about the device, and research the history of the device. Find out why people like it, what they like about it, what they don't like about it. And really important, talk to expert users of the device, because they will be able to give you some invaluable input onto what makes this particular piece of equipment worthwhile as a project. When you've done all this, then you're ready to define the scope of the project. And when I say define the scope of the project, what I'm referring to is looking to see what you actually want to model from that particular device. What are the characteristics that you like? Is it going to be suitable for a digital audio workstation environment? Is this going to fit in with a modern digital workflow? You may not want to model every nuance of a complex system. You may want to take parts of it. So this is really kind of, in my opinion, an invaluable step in looking at complex devices and how to approach them. Once you've done that, what I tend to do is then I will study the schematics, and I'll have a look and see what's going on at a component level, see how things are put together, how chains are formed, what types of components are being used, what's the heritage of those individual components, what's the history there, is everything working correctly? If you have your schematic, you can tell whether or not things should be functioning in a specific way. Schematics aren't always available, but they are obviously an invaluable tool if you do have them. And then we get to move on to our nonlinear approaches. Then what you'll need to do, or what I do, is gather the tools that you're going to use to identify your system. And when I say identify the system, because you're dealing with a nonlinear device where your output's not proportional to the input, you need to find out what's going on, what's it doing, how is it responding to signals, what kind of signals are causing these characteristics to happen, how can I work with that? So system identification is a field of engineering in itself. And is with a system like this, sometimes you'll hear people refer to it as black box or gray box. It's a way to start building information and start building a data set on how your device is functioning. So some common tools that can be used to do that. Matlab, for example, they have a system identification toolbox. And there are other toolboxes that we'll be looking at shortly to kind of go into that in a little more detail. Methodology like NARMAX, nonlinear autoregressive moving average model with exigent. You say it's a mouthful, but NARMAX is the terminology, the abbreviation. Neural networks. So you'll hear a lot of reference to machine learning, AI, that kind of thing. Neural networks can be used to identify your system, to work with your system, and to build models of your system. And then something that we're going to be looking at today is fuzzy logic. And I'm going to be running a little demonstration on how you can use fuzzy logic with nonlinear systems to solve a relatively simple problem. So these are all methodologies I've used personally in plugin development, software development. We don't have time to go through all of them, but be aware that they are out there, and further reading on these is highly recommended. But looking at fuzzy logic in particular, that's what we're going to be looking at today in terms of working with a nonlinear system. So fuzzy logic is a way to map an input space to an output space, essentially. And the great thing about fuzzy logic is it's intuitive methodology with minimal mathematical complexity. There is complexity there when you're using fuzzy logic, when you're implementing it. It is very intuitive, and you're not going to be necessarily bombarded with mathematics and all that kind of stuff. It's a very logical approach to learning about a system and mapping input to output. It's quick, it's powerful for handling nonlinearity. It's scalable. You can make the systems as complex as you need to, but in essence, it's a fairly simple tool set to work with. And you can train certain systems that you make with fuzzy logic methodology with data sets, large data sets. You have a lot of control over what you're doing. So it's a really great scalable system, and I would recommend that if you're unfamiliar with fuzzy logic, or if you're interested in how you can use it to identify systems and solve problems, then it's something that's definitely worth reading up on. And I'll share a link to some good useful text at the end. So I'm not going to spend a lot of time going through the finer details of fuzzy logic and what it is. We'll see through a working demo how it kind of works, or what it's doing to solve problems. But essentially, it's based upon the concept of precision versus significance. And this is my favorite fuzzy logic kind of visual. So you'll see precision on the left-hand side and significance on the right-hand side. So you have a complex system. This example, someone saying a 1,500 kilogram mass is approaching your head at 45.3 meters per second. That's the precise definition of what's going on. But the significance in the real world is, of course, look out, because it's going to land on your head. So what you're doing is you're really taking that precise, complex system and pulling from it the data that you need, the data that you really significant data that you need to address a problem or solve a problem. So I'm going to jump into a Matlab demonstration. We're going to be looking at a specific problem in audio, which is noise cancellation. The reason I picked that, it's a nice visual way to show fuzzy logic in action and to show how nonlinearity can be processed and how we can work with it and the tools that are available to do so. So I'm going to jump into Matlab and we'll talk through each step as I run through it. So here's my Matlab environment. For those of you who aren't familiar with Matlab, it is a incredibly powerful program system that lots of engineers use, particularly with the work that I do. I rely heavily on Matlab and the toolboxes that they have within them. This particular version of Matlab that I'm running, if you're interested, is the 2020 release 5 edition. And I have some toolboxes that I'll be referring to within these demos that, and I'll give you information on those. But if you're not familiar with it, just kind of follow through what the process here. We're not going to look at the syntax of the code too much. It's really just jumping through a few steps just to give you a visual idea of what's happening and how you can use toolboxes like fuzzy logic. So with our noise cancellation problem, we're going to set up a few parameters before we begin. And step one, we're going to generate an information signal. So the information signal is the important, significant information that we're looking to obtain from our eventual noisy signal. So I'm just going to run through each section at a time, and we'll run through and gather data as we go. So what we're doing here is we're producing a simple signal here. So this is just a sine function with an exponent. We can see there's the sine wave there, and it's reducing in amplitude over time. So this is the signal that we're going to be interested in. Now, for the purposes of this exercise, we've created this signal, but in the real world, we wouldn't know what this signal is. This is the signal we're interested in, but we can't yet see it. So we're just setting up some parameters. So here's our information signal. This is what we want to hopefully end up with at the end. And of course, because we're in the real world, we're going to need some background noise. So there's always noise involved when working with signals. And so in this case, we're going to generate some random noise for the duration of the signal that we have here. So if we run this section, okay, so we have our now lovely looking random noise signal. So what's going to be happening is we have our information signal, we have our noise source. Now, rather than just having noise with a signal in there as well and trying to pull it out, what's most likely going to happen is that you are going to have what I call here an interference profile, where your information signal is going to be is going to be picking up noise, if you like, in a nonlinear way. So it's not just a case of having that noise overlaid on the signal. There's going to be some kind of nonlinear relationship between that background noise and the signal that you're intending to work with. So we're going to use a nonlinear equation here. And this is I don't want to say simple, but it's a nonlinear equation that will generate a noise profile for us. So if we run this section here, don't worry too much about the mathematics, but all we're doing is we're just plotting this function on a graph to have a look and see what it looks like. So if we run this section now, okay, so we should have our lovely nonlinear interference profile. So as you can see, through glancing immediately, you can tell not just by the form of the equation, but now through a surface plot, we can see that we have a nonlinear profile here. And this is the profile that we're going to be applying to our signals that we're interested in working with. So we're going to call our interference signal, which is a function of that nonlinearity and the random noise signal we created earlier. I'll run this section here. Okay, so we have our original noise source, which I've called N1. And underneath we have our interference signal, which is now that noise or that nonlinear equation, which we've run our noise signal through in order to produce this interference signal N2. And what we're going to end up with is what I'm going to call a measured signal, which is the sum of our information signal, that sine wave that we plotted at the beginning, and the interference signal, which now has our nonlinear component. So when we plot this section, this is what we end up with. So in the real world, we would have had two things available to us. We would have had we'll assume that we could have measured our background noise signal, our random noise signal, and we would have been able to measure this. Now this is our original information signal with that horrible nonlinear noise profile in place as well. So you can kind of see by looking at it, you can kind of see some peaks here where it kind of follows the original exponential sine wave. But when we get past really time t of 1.5, it's very hard to make out any kind of sinusoidal wave there or any kind of value that we'd be interested in. So this is where we can use the fuzzy logic tool set within Matlab to work with that data and to calculate or to estimate our original information signal. And we're going to use something called ANFIS, which is Adaptive Neurofuzzy Inference System. We're not going to delve into how that works or the mathematics behind it. We'll keep it very, very simple. But what we're going to do is we're going to feed in our original noise signal, our measured noise signal, with our measured information signal. And we're going to try to calculate that nonlinear relationship between the two with an aim to pull out a clean set of data. So the first thing we're going to do, step number 6, we're going to define our training data, which is our noise signal, our measured signal, and we need a delayed version of our noise signal to run through the blocks. So we'll just run this section. That's done. We'll move on to our next section. We're generating that inference system object. So we're setting some parameters here, some options through the genfis command in order to create our input inference system block. So if we run this section now, you can't see much happening in the background, but with Matlab, we don't have it in a particularly verbose mode right now. But these things are happening in the background as we get towards our goal. Now what we're going to do is tune the inference system object using the data options that we've just defined. So I'll run this section. You see now we have some data coming back from Matlab where it's specifying the number of nodes, number of linear parameters, nonlinear parameters, fuzzy rules. Don't worry too much about that. What we're doing here again is to get a visual representation of what it's doing. And you see it's reached an acceptable degree of training on the 10th step. Now we're going to evaluate the model that we've just trained. And what we can do now is we can plot the actual value of N2, which was our background noise, and that nonlinear component that we defined earlier. Plot those together so we can see the actual against the estimated. So when we run this section, you'll see at first glance, it's kind of difficult. They just look like two very noisy signals, but you will see some similarities between the two. So on the top, we have that actual N2 noise profile, noise signal that we generated, and underneath is the estimated N2. So this is what the fuzzy logic, the inference system block, has calculated or estimated that the nonlinear relationship will be. And that's much easier to see when we go to our final step, which is plotting the original data signal, the one that we defined, the sine wave, against what our fuzzy logic system has estimated to be the case. So when we run this section, okay, so we have two plots here. It may not be very clear to see, but in red is our original sine signal with the exponent. And overlaid in blue is the measured signal that our fuzzy logic toolbox has taken from that very noisy data set that we had. That's what it's calculated. Now you'll see there are some kind of anomalies on some of the peaks here, and a couple anomalies on the bottom here. This is just from one round of training. So a very, very quick training round. We haven't tuned our parameters, we haven't tweaked our parameters, but we've got a pretty good representation of signal from our noisy measured signal just through using some tools that are readily available in the fuzzy logic toolbox within Matlab. So jump back to the slides now. So again, here's a summary of what we just did. It's sometimes a little bit difficult to follow any kind of Matlab demonstration. But on the left-hand side here, we have our noise signals. This is our background noise signal that we can assume we would be able to measure as part of a noise cancellation system. In the middle, we have our measured signal, which was the signal that the information signal that we measured with that nonlinear component of noise signal embedded into it, if you like. And then the third step on the right-hand side is what I call the recovered signal. And that's the signal that our toolbox, our inference system methods have allowed us to derive. So you're probably thinking, that's great. How do I model my vintage EQ? After all, you've said in a nonlinear way. Well, there are starting points that I would recommend in tackling any kind of nonlinear system. If you've been able to follow any of what I've just done, you'll realize that there are that Matlab, for example, shows there are a lot of potential avenues that you can start to explore in order to tackle your nonlinear problems. So specifically referring to Matlab, the toolboxes that I use on a daily basis when I develop plugins are the signal processing toolbox, the audio system toolbox, the system identification toolbox, and the fuzzy logic toolbox. I have some others, but these are the toolboxes that I rely on a day-to-day basis. And one of the most important add-ons for me is what's called Matlab Coder. So when you're doing your R&D work in Matlab and you're coming up with solutions to problems, you have your solutions for fuzzy logic or neural networks or system identification, what you of course want to be able to do is take those into C++ and use in your JUCE projects, for example. A Matlab Coder allows you to do that. And in combination with the audio system toolbox, you can actually generate JUCE projects. So you can generate a JUCE file, which has all of your source, which will, in theory, build on first run when you open it in Producer and then your IDE of choice. So MATLAB Coder, very, very powerful tool. The MATLAB Coder does require you to have a professional license of MATLAB, which can be expensive, but if you're a new business or you're starting out a new venture, it's always worth contacting MathWorks because they can quite often do some, make some allowances for you, set you up some demos, and identify a price point for you. The other toolboxes can be accessed using the home version of MATLAB. You're not allowed to produce anything commercial with it, or you shouldn't produce anything commercial with the home version. But if you want to try them out as demos and for your own personal projects, then the home version of MATLAB is affordable, and these toolboxes are available to you as well. Now, if you don't want to use MATLAB, there are some alternatives. So Octave is is similar to MATLAB. It's cross-compatible. It's through GNU, so it's open source. You can use it. You don't have to pay any royalties if you're using it for your projects. And largely speaking, cross-compatible with MATLAB. So it's designed so the syntax is somewhat interchangeable. I've worked with people who use Octave over MATLAB. They prefer the environment, so that's definitely something to check out. Another one is Scilab. It's a little different than MATLAB in terms of syntax, but is again a powerful tool if you do want to look into that one, and again, free to use. I quite often get asked what books whether I recommend for starting to work with nonlinear projects and audio DSP and engineering. This is a great one. Fuzzy Logic with Engineering Applications by Timothy J. Ross. Really, really useful, has some great examples of nonlinear problems in there and how to solve them with fuzzy logic. And then there is nonlinear programming. And a word of warning on this book, it is, I have my copy here, it's not for the faint-hearted. It's a very vast book. There's a lot of, you probably can't see, but there's a lot of very, very in-depth nonlinear mathematics there. So it's not for the faint of heart, but it is a really great resource when you come to working with, you start working with your really, really complex systems and design. So it's a useful resource to have on hand. And that's really all I have. Feel free, obviously there'll be a Q&A. Feel free to reach out to me personally if you have any questions you don't want to ask now, or you want any more information about any of this, matt@phillipsaudiodesigns.com. But I will hand back now. Thank you all very much for staying with that, and hopefully it made some sense, and hopefully it gave you some ideas on how you can start working with nonlinear audio and the tools that are potentially available to you.
Thank you very much, Matt, for your talk. Thank you very much, Matt, for your talk. Can you hear me now? I was muted. Great. So we have a couple questions, and there are some of them are around kind of the same subject area. So do you happen to know if there's any sort of C libraries for training and running these type of models?
That's a good question. I haven't used any specific C libraries for running and training these models. I rely very heavily on MATLAB and those blocks in conjunction with MATLAB Coder. So I'm generating C++ and C from the C libraries from the work that I do within MATLAB. I'm sure there probably are some great resources. In fact, it might be worth checking out the Fuzzy Logic book that I recommended. I think I do recall some reference in there. If you can, I always suggest that people start with MATLAB, even if you're just running the free demo for a little while to get your kind of head around the toolboxes and how it works. If you don't want to make that leap and purchase a license, then Octave is a great way to move forward. MATLAB documentation is very useful. So you can kind of derive in a lot of times what you want to do from documentation that's already online, from MATLAB documentation, etc. It's a great question though. I would recommend checking out the Fuzzy Logic book that I referenced. Great.
And another question was if there were any sort of, if you knew of any sort of Python or Octave equivalents of the Fuzzy Logic toolbox. You happen to know
So
any?
the individual toolboxes within Matlab, they don't always translate directly into Octave for obvious reasons. You know, they're commercial products. But there are, Octave has a really, really active community. So if you're looking for specific, for example, neural network system identification or fuzzy logic routines, functions, then jump into the forums on Octave, and people will quite often share their solutions. It's a very, very friendly community. So I would, although offhand, I don't know of any particular project names for any kind of any of the toolboxes I directly use in Matlab. It wouldn't be surprising if there are already solutions out there that are very, very similar to the tool sets that are in Matlab.
Great. Sid asks, why fuzzy logic over using neural networks?
That's a great question. So one of the advantages of using fuzzy logic is that you get a very, very quick and sometimes, say, rough and ready idea of what you're working with. Now, it may not always be possible to solve a complete system problem using fuzzy logic, but if you're at the system identification stage and you just want an idea of what's happening, you just want to see, you're looking at perhaps one specific behavior of your system, of your device, fuzzy logic is a great way to go about mapping that, visualizing what's happening. With neural networks and lower level system identification, that's when you can really drill down. I mentioned the training sets and the training iterations. That's when you quite often need to switch into one of those lower level approaches. So fuzzy logic it's great because it is easy to use, it's easy to understand, it's based on really human vocabulary more than anything. So and as you saw from the example, just a few Matlab commands allowed us to recover a signal from a lot of noise. So I guess you wouldn't necessarily use logic to solve a complete project, but it is a really, really great starting point, in my opinion. It's one of the things I do to get an idea of what's happening at a system level.
Great. Max Keen asks, are there any nonlinear systems that are being created that are novel, i.e. not emulating something analog?
That's a great question. That's a great question. The answer is yes. I'm working on one. I can't say any more than that. But you can really, there's a lot of creativity within DSP when you're not looking at an existing piece of hardware, when you don't have you're not constrained by rules and how people are going to perceive or A/B the original project against what you've done. So yes. Other examples I'm trying to think of that have done that. There are a few very novel plugins that if a plugin house or a plugin developer mentions neural networks or AI or machine learning, then the chances are they've used some nonlinear mathematics, nonlinear approaches to create a new tool. I don't want to call out specific company names, but there's lots of really, really cool research and lots of great products. But look for those keywords. Look for things like neural networks, AI, and products that aren't referencing a vintage device, for example. But there is work being done, and as I say, I'm working on something. I wish I could tell you more. But yeah, be creative with nonlinear DSP, and don't use it just as a solution to a problem. Use it as a creative outlet as well.
Great. Joe Black asks, how do you deal with different sample rates in your training if your training happens in Matlab?
Different sample rates. Well, it's a good question. Now, you really, with the fuzzy logic example that I showed, because you're learning about the system as a whole, you're effectively you want to deal with your well, the way I approach is I deal with my highest sampling rate first. So I want the highest resolution version, if you like, of what I'm looking to analyze. manipulating sample rates themselves, that's really more of something that I would approach once I have my models, once I have my behavioral models, if you like, from the system identification that I've done, and that becomes more of an audio problem and less of a system identification problem, I guess is my answer there. So sample rates are really, I guess you could think of them as being a lower level in the process. So get your data set of whichever resolution you deem to be the best, however you're going to manipulate it, depending on how the resources you have to run through the training, computing power or whatever your approach is. And then once you have your reference models, that's when you would look at the things like sample rates and those kind of more audio stack related issues. I think that's what you're asking. I hope that makes sense.
Great. Sorry, that's my dog itching. Wait for her to stop. Okay. Joe also asked, what's your opinion on machine learning versus circuit-based physical modeling for nonlinear processing?
Awesome question. That's an awesome question. I don't want to be diplomatic about it. I actually think they go hand in hand. Now, have I modeled systems where I haven't had schematics available? Yes, I have. And I think there's a tendency when you have schematics in front of you and you start looking at nonlinear behavior on a component basis. So let's say you're looking at a Carnhill transformer from a mic pre. And you spend all of your time modeling that one specific component and before moving on to the next stage of the circuit design. I think there's a tendency to kind of get lost in the really, really low level design of a product. And that's when I suggest I mentioned taking a step back. So quite often you really want to concentrate on what you actually want to get out of that model. And quite often it's, I prefer not seeing the schematics to some extent, because I can take a step back and really listen to and learn about the project and capture the characteristics without getting bogged down or tied up at a schematic level. And that's not always possible. And of course, there are instances where you need to look at individual components. But I would say with the advances in toolboxes that are in Matlab and the advances in just AI machine learning methodology across the board, I think learning about systems, identifying systems outside of the schematic realm is becoming more and more doable, more and more accessible to those who might not have the analog electronics knowledge prior to taking on a project like this. So that's an awesome question. They both have their merits, but I think, I'm going to say it, I don't think you necessarily have to have a schematic before you approach the problem.
Great. We have another question from Sid. Can you share more about your approach for choosing appropriate stimuli for system identification?
Good question. So that really comes down to the type of project that I'm working with. So if I have let's say an IC-based EQ, which isn't designed necessarily to take a really driven signal, then I'm going to choose an input signal input stimulus, which is appropriate and relative to that device. If I'm working with a mic pre, for example, then I'm going to want to find out how people are using it. And this goes back to when I was saying that you want to talk to people who've used that particular device, the expert users. Find out how they're using it. Find out if they're using it off spec, I like to say. So a lot of great sounds throughout history of recorded music have come from people experimenting and driving things harder than they were designed to be driven. So base your stimuli on that. As far as actual stimuli signals, I use a whole range. So everything from white noise to sine waves, impulses. It really depends on the section of that device or the area of characteristics on that device that you're concentrating on. That's what type of signal you use. And of course, ultimately, you're going to be using real world signals, so actual recorded audio, driven audio, that kind of stuff. So use a combination of input stimuli when making models, when identifying systems. Don't tie yourself to one particular way of approaching it. Don't use white noise for everything, pink noise for everything. Use change the entropy of your input signal, because a lot of the times if you have if you have kind of time varying noise gates that you have with Rupert Neve devices, for example, hysteresis, then you want to vary the entropy of your input signal, of your input stimulus, because you want to be able to see how that entropy is, of course, another variable that exhibits nonlinearity in a lot of these devices. So, so choose your input signals carefully and kind of match them to what you're trying to understand from that particular device or that particular stage of the device.
Great. I think that's all of them. Thank you very much for your time, Matt. It's very,
thanks, Josh.
very
Great to be here.
interesting.
Yeah, thank you for this wonderful talk, and thank you for these really insightful answers to all these interesting questions. That was really quite fascinating.
Yeah.
Yeah. Should we go on with the next talk? We actually have more DSP related content for you tonight.
Yeah. Not nearly as complex as Matt, but I thought I'd have a little stab at it tonight, see what we could do. So yeah, I don't think we need to do an introduction or anything. I'll go ahead and share my screen. So this is a talk more for people like myself that are just really kind of starting out. We're just kind of getting our feet wet with JUCE and with DSP and with C++. And so I thought I'd make a talk that's an introduction to the JUCE DSP module. So can everybody see my screen okay? Yeah?
Yes.
Great. Okay, great. So this is just a brief introduction to the JUCE DSP module. And as you may know or may not know, JUCE 6 was released recently, I think about a month and a half ago. And so I thought that it might be nice to give a talk on some of the things that are new in the DSP module and a little bit about how to use it. So here's an outline of what we're going to talk about today. We're going to give an overview of the JUCE DSP module. And in the JUCE DSP module, you have widgets and you have processors. We're going to talk a little bit about the differences between those two. And then I'm going to show you just a very quick overview of how you would make a quick widget and another one where you would make a very simple processor. And then we're going to have a Q&A. So this is more almost of a lightning talk. Shouldn't take very long. So what is the JUCE DSP module? So the DSP module is a way that we're able to create abstractions very quickly. So rather than having to write a delay or a chorus or a filter on your own from scratch, which would take a very long time, especially if you're just learning, the JUCE team and some other people such as Ivan Cohen, who's a DSP engineer over in France, have taken the time to actually write some of these abstractions for you, some of these algorithms, so you don't have to start from scratch. And you can actually take these and you can, they're little blocks, they're almost like blocks of code, and you can take them and you can actually put them together quite quickly. So this concept was originally introduced in 2018, and of course, there are other libraries that are out there that do the same sort of concept, such as Maximilian. And in the JUCE 6 release, there have been various improvements to the original DSP module. One of which, off the top of my head, was that in the original module, you used to have to use what's called process duplicator to duplicate the DSP process manually for each channel of audio that you have. And for these new algorithms, you don't have to use the process duplicator anymore. And as I said before, the module consists of processors and widgets. And if you'd like to have a look at the JUCE example, the official JUCE example, which is written very well, and it shows you pretty much all of the DSP, blocks that are available to you, you can actually check it out. If you have JUCE downloaded, you can just check out in the plugins folder. There's one called DSP Module Plugin Demo, and that has all of the algorithms, and you can just switch in between them and try them out. So what I wanted to do is I wanted to pick out just 2 of them and just break them down and show you just the workflow of those. So as I said before, you have these 2 types of blocks of code in the DSP module. You have the processors, which are essentially like small blocks of code. You can't really use them on their own. They have to be used in tandem with other DSP effects or with other algorithms in order to actually create a whole effect. And then you have what are called widgets, and widgets are kind of self-contained DSP algorithms that you can actually use on their own and actually build a simple plugin just from using these widgets. And so what's the first thing you need to do in order to actually be able to start using this? So the first thing that you need to do is, of course, download JUCE if you don't have it. So for people that don't know, JUCE is a cross-platform C++ library for creating audio plugins and apps. So cross-platform means that you can write for Windows, Mac, iOS, and Android from one code base and deploy to all those different platforms. And it's a very powerful tool. So once you have JUCE downloaded, in order to actually start using the JUCE DSP module, you actually have to add the module. So what you see here is your producer in front of you. And what you would do is you would click the plus symbol there that you see down in the bottom left-hand corner. Then you just click add a module, and then you can go to the JUCE modules path and you just add the JUCE DSP module to your modules. And those are kind of like your toolboxes that you're using to actually create your code. So what we're going to do really quick is we're going to go through a widget overview of a chorus plugin. So this is a very simple chorus plugin, and this is a great way to show you the workflow of how you would use one of these widgets to actually create something that you can actually load up in your DAW and use as a DSP effect. So the first thing that you need to do is you need to go to your header file, and you actually just need to instantiate a chorus DSP object, and that's how you would do it. So you would use JUCE DSP chorus, and then you could use either float or you could use double precision audio, and then you just create an object there. From there, you have a function that's called prepare to play, which is a function that calls when you're about to start playing the audio. So it just ensures everything's in the right place. All of your DSP algorithms have been reset and back to there's no kind of junk audio kind of hanging around in your buffers, and that it ensures that you're clean and ready to go. So to start off at the top, you have a object called a spec, a process spec that needs to be instantiated. So the spec is a way that you can let your DSP algorithms know what sort of buffer size you're dealing with and what sort of sample rate that you're dealing with. Okay, so by sample rate, what I mean is that if you're calculating at 44,100 samples per second, your DSP algorithm is going to have to process that amount of audio versus if it has to calculate at 48,000 samples per second. Okay, and that's what's so important for these DSP processes to know. They have to know how many samples that you have to actually calculate a second. From there, we just pass that spec object into our chorus object that we created, and then we just reset it, make sure that there's no junk audio in our buffer. Also, we have these parameters that we can create. So you can find all of this, what sort of parameters in these DSP widgets that are available to you just by looking at the JUCE API that's on juice.com. And so you can see here that we have some very basic functions that we can call. So we have one called set rate, we have a depth, center delay, feedback, and set mix. So the way that you would normally do this is you would create a slider or a dial for each one of these. Then you would attach it normally using an audio processor value tree state, okay, which is something that is beyond the scope of this particular talk, but you can actually find tutorials on this on this channel. So once you've created your parameters, you've hooked them up to your dials, you've set the values of what your minimum and maximum of each one of these parameters are, then you're ready to go. And another thing is that you can also click into these functions, and normally there will be some sort of hint about what sort of minimum and maximum that what sort of values that these functions are expecting. From there, we're ready to go to our process block. So for people that aren't familiar, the process block is where your audio is actually processing your input and output. So it's the main guts of the audio for your plugin. So what we have is we have an audio buffer, which is responsible for outputting the audio. So that's kind of like your train where you're actually taking audio and you're bringing it through. And what you're doing here is we're actually creating a sample block, which is a reference to our buffer. And then what we're doing is we're processing the audio through this chorus effect. So when it says chorus.process and it has process context replacing, what that means is that all of your audio is being processed through this chorus plugin, and that is actually replacing what's in your buffer, and that's what you're hearing through the output. So that's how a widget works. And now I'm going to show you a little overview of how a processor works. So as I said before, widgets are more kind of self-contained DSP blocks where you are able to kind of create a plugin just using that one object. With a processor, it's a little bit more complex in that you have to use a couple of these together with each other. So they're smaller blocks, and you actually combine these to make a bigger abstraction. So for this one, we're going to use three processors. We're going to use the delay line, we're going to use the linear interpolator, and a dry wet mixer processor. So now we're going to instantiate these objects. And as you can see here, we have an effect. We have this const expr called effect delay samples is at 192,000 samples. Okay, so you may be asking why 192,000 samples. Well, the reason is because if our max audio sample rate is 192,000, I think that's what it is, then what we need to do is that accounts for 1 second of audio. So most sound cards, the max sample rate is 192,000, and so 192,000 is the accounts for 1 second of audio, and that's where we're going to store our actual delay samples. So then what we're doing is we're instantiating these delay lines with the effect delay samples, and then we are instantiating our dry wet mixer. So that's just going to be where we're going to have dry signals coming in, and then we're going to use the mixer to actually mix it with the wet signal. Then we're creating these arrays that are going to kind of hold our delay values. So the reason that we're using an array of 2 is because we have a stereo signal, we have 2 speakers, and then we have feedback if we want to take the feedback and we want to feed it back into the delay, so we hear more than one delay. And then we have a volume control that's going to control how loud the volume is going to be of that feedback. Then once again, we're back to prepare to play. Once again, prepare to play is where when your audio is getting ready to start playing, so when you're about to start processing audio through your plugin, prepare to play calls, and this just ensures, once again, that all of your DSP algorithms are cleared out, they're ready to go, and we have that DSP process spec object that we have to create again, because we need all of our DSP algorithms to know what our sample rate is that we're operating at. Then we have our parameters. So in this case, we have 3 parameters that we're working with. We have a rate parameter that defines what the delay rate is going to be. We have the mix, which is going to mix between our dry and wet signal, and then our feedback, which is going to define how long the feedback of our delay is going to be. So now here's our process block, and I had to divide this up over 2 slides. And so what we see is that we're creating this audio block reference, which is a reference to our main buffer. And what it's doing is we have that 0, which is the start channel, and then we're doing the number of channels that's in our audio, which is going to be 2. And then once again, we're doing the DSP process context replacing, which means that we are replacing the incoming signal with whatever we get from our outcoming signal. Then before we start actually processing the delay, we want to take the signal before we put it into the delay. We want to actually push it into our mixer so that we are able to mix between a wet and a dry signal. From here, this is a little bit more complex, if I know it is for me, but this is essentially a simple feedback delay. So we're going through the channels, and what we're doing is we're getting a pointer to our incoming samples and also to our outgoing samples. And then what we're doing is we have this variable called last delay output, which is essentially, if we go all the way down to the end of our for loop, we can see that what we're doing is we're just using that signal to feed it back into the very beginning of the for loop. And this is what gives us our feedback down. Then we have our linear, we're using our linear interpolation to actually, where we're pushing our samples into, we're pushing each one of these samples into our linear interpolation, and we're setting the delay, which is going to give us how far apart each one of these delays is going to be. And then we're using that to feed it back into itself. And then at the very end of the process block, we are mixing that with the dry signals that we pushed in at the very beginning of, before we went into that double for loop. So we have our dry signals that we push in, and then we're mixing it with the wet samples that we're getting from this delay. So that's the end of the talk. So I hope that that helped give you an introduction to the JUCE DSP module. And here are some resources for you if you have some more questions about these. So of course, you have the JUCE forum that you go to. You could ask these questions. There are a lot of different discussions. So if you have a question or you run into a particular problem with using this, you can actually go to the forum, and normally there will be somebody that's asked a question before if it's something that's particularly difficult. Also, be sure to check out the JUCE example, which is once again the DSP module plugin demo. You can go to our Discord community, and you can find that on theaudioprogrammer.com/community. And I've also created a GitHub repository for both of these plugins for you to check them out. So I've done my best to make these as simple as possible so you can pick them apart, and you can find those here. And I'll make sure that I have these slides available in the description after the talk. Great. So anybody got any questions?
Yeah, thanks, Josh. So that was a great introduction. It's actually surprisingly easy to put together a plugin. That's pretty cool.
Yeah.
So yeah, we have someone, Joaquin, saying basically, please put more videos up on your JUCE 6, about JUCE 6 on your channel.
Yes, absolutely.
So
Yeah.
I'm also really looking forward to that. But we also have a couple of questions. So Yapikol is asking, if you wanted to create an effect that kind of fully shut off and turn back on, like a reset buffer, every time a note was played, what would be the best way to do that to avoid clicks?
So ask that again.
So my understanding of the question is that if you wanted to have something where you press a note and it turns something on, and you let the note go and it just shuts it off again.
Yeah.
What
So
would be a way to do that with, if you want to avoid clicks?
yeah, so it sounds to me like, depending on what it is, so it sounds to me like there needs to be something that's mapped to MIDI events. So you have, when you're pressing a key, you're going to have a MIDI buffer that's happening in your process block. And so what you need to do is you need to detect when that's actually happening, to trigger an event. Maybe it's a Boolean flag, to actually be able to make sure that a click isn't happening. So clicks normally happen for one of two reasons: either that the audio has stopped and it's in the middle of a wave and it's not. So basically, the waveform is giving you instructions on how your speakers need to move forward and backwards. So ideally, what you want to happen is that you want your audio to stop when the speaker is in the center position. And if it stops when it's in the middle of a wave cycle, then that's when you're going to hear the click. So sometimes that happens. For that reason, another reason why you may hear clicking is that a lot of people forget that they need to normally create a DSP process for each channel of audio that they are actually processing. So, so if you have two channels of audio, like a stereo system, normally, not really counting what's happening in this JUCE DSP module, but normally you have to have, if you're doing filtering, you have to have two filters, one for the left channel, one for the right channel, and those need to be processing the audio independently of each other. So, so you need to make sure that that's happening. But what you would need to do is you would need to find a way to kind of tail off that audio. Maybe, I don't know if somebody else probably has a better, a more technical suggestion on here on this, but you would need to somehow maybe crossfade the audio, to make sure that it actually approaches kind of a zero crossing point rather than ending in the middle of a wave cycle.
Yeah, so I don't know if JUCE 6 has like a new way of doing this, but from what I remember, you had like, there was this linear smooth value, which lets you create a ramp, and then you kind of just multiply that with your signal.
Yep.
And keep it playing until it reaches zero, basically, instead of just cutting it off. I think that would be one way of doing it. There's like multiple other ways of doing it. I think it kind of really depends on what's going on.
Great.
Right, so there's a few more questions actually. So Atsushi Eno asks, hopefully that's a general question, but is it safe to assume, and I guess that's actually a question more for the JUCE team than it is for you. But the question is it safe to assume that those parameter names and those DSP classes don't change in future versions?
I mean, I would imagine so. You wouldn't want, I mean, that would be a question more for the JUCE team, but I know that the JUCE team does its best to make sure that it doesn't do any sort of breaking changes. And even with this DSP module, there have been new algorithms that have actually been rewritten, but they've still kept some of the old ones just to ensure that there are no breaking changes for people that may have used the previous version. So I can't picture a situation where they would intentionally go and break that and make it different than what it is right now.
Yeah, that's my impression as well. So yeah, let's hope that's the case. So Binder News asks, should you use float or double for samples?
Well, this is a discussion that I hear people talking about. Some people actually claim to be able to tell the difference between floating samples and double. I mean, I can't. I don't know anybody that does, and I think most DAWs actually do just floating point processing. I'm pretty sure that all major DAWs do floating point processing and not double. I may be wrong about that though, so I reserve the right to be wrong.
All right, and that's maybe, so Roberto is asking, actually that's something that we could just say to everyone, whether this video is going to be uploaded on this channel or whether it will be deleted after it has been live.
Yes, so all of these videos will be uploaded to the channel afterwards. So what I'll do over the next couple of days is I'll actually separate these out and provide any resources for the talk, so slides or links that people want to share. And so you will have the live stream, this full live stream, and you'll also have the videos separated out.
All right. And I imagine that with the other issue with the fading out, it's actually someone mentioned an ADSR curve there on the chat, which is, you know, kind of the next thing you would do. So I guess you
Yeah.
have tutorials about this kind of stuff on your website, don't you?
Yep. We have a JUCE tutorial. We have a tutorial on the ADSR object and how to implement that for sure.
That's great. So yeah, I guess that's an amazing resource if you want to know more about this. Yeah, I don't see any more questions to you on the chat. So
Great.
yeah, I think we're ready for the final talk of the evening. So for the final talk of the evening, we have Spencer Salazar, the CTO of Output, who's joining us tonight to talk about his PhD project, which is Orglyph, modular music sketchpad. So really curious what that's going to be about. Hello, Spencer. How are you doing?
Hello. Thank you for the introduction. I'm doing well, thanks. Yeah, and thank you, Matt and Josh, for the interesting talk so far, and Celine as well for kind of giving us a little bit more detail about the Audio Developer Conference. I'm certainly looking forward to finishing up my application and seeing everyone else's, what everyone else has to present. Last year's was certainly really a lot of really interesting talks. And I also want to thank Josh and Teamer for hosting this. You know, like having this kind of community is just you know, really amazing. So appreciate all the work you guys do.
Thank you very much.
Yeah,
So yeah, totally. So yes, I'm the Chief Technology Officer at a company called Output. We make music plugins for your DAW, such as Arcade, which is sort of like a sample playground. Portal is kind of a granular effect. Thermal is sort of more of like a kind of multi-band distortion type effect. These are all really cool, really fun. And if it's okay, I will also mention that, you know, we're always looking to hire cool software engineers if that sounds like it's up your alley. You know, we have a lot of really interesting challenges in the world of audio development, and hopefully I'll get to talk about some of these at some point. My talk today is going to be about something that's totally different, which is my PhD thesis. I graduated from my PhD program about 3 years ago, and the project that I worked on was basically something called Orglyph, which is what's being called a modular music sketchpad. And maybe to just kind of kick things off, I can go ahead and share my screen, and we will see the presentation. Cool. So Orglyph is a modular music sketchpad. What does that even mean? Sometimes I wonder that myself. Maybe after this talk, you will know, and maybe I will know as well. So basically, my backgrounds especially are in kind of two major areas. Besides audio programming, specifically related to mobile devices, as well as music programming. When I was an undergrad, I started working with a programming language called Chuck, and built like a lot of the sort of core technology within Chuck. If you ever used it before, it's a pretty fun one. I recommend checking it out. It's been used for things like live coding in some cases. It's kind of like in the heat with things like Super Collider and Tidal Cycles. As well, I worked for a mobile music company earlier in my career, basically making iPhone apps for music, including one called Ocarina, where basically you would blow into your phone and play it like a flute. And we also made like a auto-tune app for T-Pain. So kind of like two different aesthetics there, but both really important parts of my my personal background. So what, did I skip something? Okay. So what about programming? Let me just like, that's actually kind of a key point in the presentation. So let me set that up a little bit. There are like a ton of cool apps for music making, and probably people who are listening right now, you know, you've either made these or used these. I love all the stuff that AudioKit is doing. Moog has like some amazing music apps that they've released. There's too many to name really, and it's really exciting to see basically mobile music and music apps for your phone or iPad or whatever really exploding. But the question I kind of came to was like, what about programming? One day I was basically just sitting with an iPad, messing around, making a bunch of cool music and stuff, and I was like, the only thing I can't really do with this is program. So how do we kind of like solve that problem? Is there like is it crazy to think that you might be able to program with an iPad? And kind of more to the point, can we even empower creative coding using mobile touch technology? Can we not just have like, yeah, I guess you can program with this, but like, yes, I totally want to program with this. This is amazing. Like, I love programming with this. Basically, can we make a system for creative programming that's in some way better using an iPad or a phone, and really use the capabilities of the touch screen to somehow make coding better? And if you think about it, it's a little bit crazy because when you think about how you work as a coder, you're constantly typing. So without a keyboard and without like an actual physical keyboard, you're kind of there's not that much you can do, I guess, and it can be sort of limiting. So this was sort of a crazy idea. Fortunately, I was trying to get a PhD thesis, and they love crazy ideas in the academic world. So I went with this. A little bit of background. I touched on this already, but the kind of two areas of my background that have informed this are what you see on this side. This is Chuck. This is what a typical Chuck program looks like. I've been working with Chuck for forever and been part of the core team, basically working on this music programming language. So, I like to think I know a thing or two about music programming. As well, kind of mobile touch technology on the other side here. This is one of the modes of Ocarina where you can see, you can't really hear it right now, but you can see people playing. This is someone, looks like in Sweden somewhere, basically playing their phone, and we can, you would be able to hear this in theory. For now, we can just see it. So this was like a mobile phone app I worked on, really like in the first, this came out like the first year that mobile phone apps were a thing for iOS at least. And that's not to say there aren't systems where you can basically do programming on your iPhone or your iPad. Like Codia has been around forever. It's popular for making games, and they've since released something called I think it's called Shade, which is actually like very similar to what I'm about to show, which is really cool. Swift Playgrounds has been kind of more aimed at education and kind of people who are pretty new and kids really. Touch Develop is actually a really interesting project from Microsoft Research, where they kind of like started out with similar goals. Scratch as well is kind of a little bit more, again, oriented towards kind of younger people. But again, like this is programming. You can do this on a touch screen. The React table, of course, is something that I think is really influential in terms of like the work that has gone into Orglyph. But I guess you could sort of ask, like, is the React table considered programming? That's a question maybe for the audience, or at least to maybe provoke some discussion. So to start things off, I was like, okay, well, I know what Chuck is, and like I know how to use Chuck to do things. So let me just make this on the iPad. So this was something I made kind of like sort of half expecting it to not be that successful. And I don't really use this too much, and this has never been released. It's open source, so you can go download it right now from my GitHub if you want. But I was like, let's see how bad this is to actually type code on an iPad. And I wouldn't say it was great, but it did exist, and maybe it partly proved my point that like typing isn't really the answer here. So then I thought about this. This was all like kind of starting around 2013. The machine learning renaissance was back in full swing. There's so many libraries you can download for gesture recognition, especially for handwriting recognition. The post office has been doing handwriting recognition on, your mail for decades at this point. So you can just go download like 10 different handwriting recognition libraries and put them in your code right now. So I kind of put two and two together and was like, what if instead of typing code, you can actually draw your code or write your code like with text? And so I kind of ran with that a little bit. So let's take another step back. This idea of sketching code, I think, was pretty intriguing to me. And the idea of sketching in general, I think, is actually really interesting from a musical perspective. We can go way back, but just taking it to, you know, in the 1950s, there was a Canadian animator named Norm McLaren who produced an Oscar-winning film called Neighbors. It won for, I think, Best International Short Film, where he basically painted little blobs on the soundtrack portion of film to produce the soundtrack. So this was kind of one of the first cases of someone actually like drawing something that's then kind of transduced into sound using some kind of electronic medium. Daphne Oram, another very like well-known example. She was working with the Radiophonic Sound Laboratory, and basically she had this crazy setup. There's an app that you can download actually that my friend Parag helped make. Really cool app that basically kind of simulates a lot of this. Ivan Sutherland had this was not really music related, but he kind of like explored this territory a lot as well, basically drawing different things into kind of like a touch screen and being able to manipulate it. Here's Ivan Sutherland basically drawing waveforms. That's Max Matthews, who many consider to be the father of computer music. They were kind of plotting different things and listening to what it sounded like way back in the 1960s. Yanis Xenakis had a really interesting system called the UPIC or UPIC. I forget what it stands for. But basically, this was pretty cool because you could actually, on this panel you see here, you could draw two different things. You could draw the low-level waveforms. So you would draw like what the actual waveform looked like that would be cycling over and over. And then you could also draw basically how these waveforms would be mapped to frequency over time. So it was kind of like both the microscopic level as well as kind of the macroscopic kind of compositional level. Really interesting device. Actually, a book just came out about it, like a retrospective as far as like not just the device itself, but the impact that it's had on the musical community. This is Herbie Hancock and the Fairlight CMI. The CMI actually allowed you to draw in waveforms and play them back. It was probably one of the earlier wavetable synthesizers, and you could actually draw wavetables. I don't know if Herbie Hancock used this a lot, but it is sort of similar to this idea of like being able to draw sound. This is Kate Bush, also a well-known Fairlight CMI user. And just more generally, I think like the idea of sketching is really interesting as far as like any sort of creative process. Whether it's purely kind of more in the aesthetic realm, like music or drawing or painting or you know, creative writing, or if it's something like, you know, let's say you have a really hard technical problem you're trying to solve, like at your programming job, you know, what do? You go, you whiteboard it and you draw different ideas and you kind of like erase some things and maybe draw something else and like try a few different ideas out. Sketching in general kind of allows you to really just explore lots of different ideas in a very sort of natural way where you're kind of in between both imagining the idea, sort of seeing it as you're drawing it, and then being able to like kind of like iterate on that. So this is a drawing I borrowed from Bill Verplank, who's like a very well-known UX designer or UX sort of theorist. I definitely recommend his writings if you're interested in any of this stuff. So I kind of put all these ideas together into something called Orglyph. And so now I will do a little bit of a demonstration. So this is what it looks like if you watch a video that I made of it, but I can do a live demonstration instead. So let me make sure this will work. I have an iPad connected here, and let's see. Everyone see that?
Yep. Yep, we
Yep.
can see it.
Yeah, we can see it.
Great, cool. So this is Orglyph. This is sort of what you start out with. It's basically just a blank canvas with just this little icon in the middle that represents a speaker.
Are you like pinching?
Yeah, so this is a pinch gesture. You can zoom in and out and kind of move around and see things. If you draw, I have a stylus here. So if you just draw things, normally you kind of get, you know, it's just drawing basically. You know, you can kind of draw whatever you want. But if you kind of switch to this other mode, you can draw things that get recognized. So this basically got recognized as like an audio node. So if you're familiar with kind of the lower level details of audio, programming and synthesis, this is basically just kind of one block in your audio graph or your audio chain. Or one module, I guess, in your modular synthesizer. And there's a whole bunch of different options. There's these sort of abstract symbols, and there's somewhere else there's a reference for these, so you can kind of understand what they all mean. But I think we can probably guess what this one here means. This is a sine wave. I'm going to go ahead and play this kind of quietly and then ramp it up just to make sure I don't hurt anyone's hearing. All right, good old sine wave. Gotta love them. In theory, that's all we really need, and that's all I'm going to start off with to start here. But let's go ahead and take another sine wave, and you can basically map kind of anything to anything. There's a lot of modulation possibilities here. So now I'm doing basically AM, amplitude modulation. And let's make this a little bit higher pitched. Okay, AM is cool. Let's get some FM in there too. I love me some FM. And let's crank the gain on this. I'm gonna crank this up to like 1,000, let's say. And let's put some more AM in there just for fun. Cool. We can keep going. Of course, we have we have a grab bag of filters, so you can see these. High pass, low pass, band pass. There's a few others, but let's try the low pass first. So it got a lot quieter, but we can go ahead and that sounds like a low pass to me. Always a crowd pleaser to just sweep the filter a little bit. And then let's change it up a little bit. So what else should we put in here? We can put this through an envelope and maybe get a little bit more of a rhythmic kind of variety. So now we're not going to hear anything. This is your typical ADSR envelope. Nothing too surprising. We do have to trigger it somehow. And the way I'm going to do that is with a different type of node. So if you draw a square, you get this different menu of different types of control rate nodes. So this kind of blocky looking thing, this is a sequencer, and you can basically add as many steps as you think you need. I'm going to just kind of play it straight with 8 steps here to start with. And then let's go ahead and trigger this. Cool. So I'm not getting a lot of variety here, but one thing I'm going to do is throw some delays in. I always love delays. And if we make these a little bit separated, get maybe just a tiny bit of spatialization. And then another thing I can do, again, we're not getting a ton of variation here, but what I can start to do is basically use blocks of control nodes to get, to build up different, to build a scale, basically. So I can use this basically to map the output of the sequencer to different scale degrees. So I'm gonna go and take this and pop this into the degree here. And then the second thing I'm going to do is, I don't really have a great icon for it, but this one right here, this arrow, is a a MIDI to frequency converter. So let's go ahead and map some frequencies here. All right, so we got some tonality now. That's kind of cool. The other thing I can do, I can make this major, minor, whatever. Put all my music theory, education to work here. And let's make this a little bit brighter. Let's just make this like 10,000. All right, yeah, it's pretty delicate right now. If I want to save this, I can go ahead and save it, and I can draw something to remember my sketch by. So I'm just going to call this Tap Meetup. And then I can continue to draw different things and like, annotate this and kind of do what I want really. And to give you an idea of kind of how you might use this in practice, I've actually kind of gone on, I'll talk about this a little bit. I've actually kind of performed with this as a performing instrument. And, this is the bass patch for one of the songs that I have. I'll write the fader a little bit so I don't hurt anyone. So this is something that I've kind of played around, different performance and DIY spaces in Los Angeles where I live most of the time. And basically, it's just a simple FM patch with a lot of delays and some all-pass filters. So I've kind of made like sort of a really basic mini reverb. You can see with the all-pass filters here and the cascade of delays, this bit is kind of a fun one. This is basically just a multiplier. So I'm multiplying the output of the delays together, which doesn't do that much normally if you're just multiplying silence or like a low level by a low level, but it does kind of make things go crazy once like the actual sound going through it is a little bit more, there's a little bit more going on. So one thing I can do here is I can control both the scale as well as basically the amount of the scale that I'm accessing. So we can see a sequence that I've made here. And as I multiply the output of that sequence, it basically kind of activates a broader range of the scale. And then what I've also set up is basically an FM patch where I can control the index of modulation, the gain here. So we start to hear these brighter tones. The other thing I've set up is all of this area over here that's very tonal is going through basically a gain control. I have this set up as a gain control, and then it's connected to the phase of the sine waves. So this is basically phase distortion. So as I increase our wave shaping, as I increase the gain here, it's actually clipping a little bit for me, so I apologize for that. I can even like add to it and get a lot of like kind of wackiness and very non-linear, that's for sure. So it's fun. So basically, like as a music performance, like I kind of have enough levers to turn there to kind of take that for, maybe a few minutes. So anyways, that's Orglyph, a brief demo of kind of all the different things you can do with it. And then the other bit, this was all part of a research project. And in the research worlds, there are basically, you kind of have an idea and then you set up you know, an evaluation, and you want to know, like, you know, is the thing you said like true or not, and to what degree is it true? And so what I was basically trying to say is that this is actually cool and usable for musical performance. And so to prove this, I basically was like, all right, I'm just going to play some shows, and if I don't get tomatoes thrown at me, you know, maybe this is a successful kind of musical instrument of sorts, or meta instrument, or at least like a platform for music creation. So I set up a solo practice. I've been playing shows. I haven't actually done any shows since kind of everything closed down here, but it was all good fun. I haven't got tomatoes thrown at me yet. It's been really fun to actually kind of like have a totally different type of musical experience to show to people. And usually when I do perform, I kind of project what I'm doing, like I'm showing you now, so that, you know, there is like this sort of like visual element that people can see and respond to. So this is one of the pieces. Oops, is there a way to turn this down? So yeah, this is one of the earlier pieces I made. And what I love is just kind of seeing all these waveforms like go all around the place. By the time this piece is over, like basically the entire screen is just full of like these waveforms that like are just too big to be represented. This is another fun one. I actually meant to show this during the demo, but there's a module where you can basically just draw the waveform itself. So this is a pretty direct connection to the sound itself, I would say, and definitely invokes sort of the ideas I was talking about earlier with, you know, having some sort of connection to the sound itself, as well as some of the interfaces like the UPIC or some of the other sort of graphic compositional tools. This is a show I played. We don't need to see that. I hosted a bunch of workshops. At the time I was teaching at a school called California Institute of the Arts, somewhat close to Los Angeles. And so I taught students this, and, you know, I started showing it to students and they became really interested in it, and I kind of like use this as a teaching platform, which was pretty cool. So this is kind of a jam sesh that some of the students were having, which is pretty fun.
Sorry, are you showing stuff on your screen? Because I'm not sure people are seeing this. They're seeing our faces.
Oh, I'm so sorry. Thanks for mentioning that. Let me go ahead and share my screen and try this over. Cool. Let me go back to, okay, so I was saying solo
Yes,
practice. You can see my
sense,
screen now?
Yes.
Cool. Thank you for pointing that out. So yeah, this is again, sorry, this is so loud. Not really. Anyways, these are a few of the pieces that kind of resulted from that. So yeah, here you can see basically drawing waveforms and having a sort of feedback connection. This one sounds great on like an amazing, like a sound with amazing bass, like subwoofer or something. Like really, really fun to hear this like through a massive PA. A little different over like, you know, my tiny little headphones. So yeah, this is sort of the result of some of the workshops. I had a bunch of concerts with the students that I was teaching at the time. This is a piece we did with audience participation. So later on, actually, the people in the audience have iPads too, and all the iPads have Orglyph. And so there's a way you can actually rent iPads, I guess, for like corporate events and things like that, where you just need a bunch of iPads. You could rent them for a weekend. And so that's what we did. And we loaded them all up with Orglyph, and kind of tried to see what would happen if, you know, all of these sort of people at this this musical event were presented with this interface. So here's where everyone joins in. You know, I wouldn't say this is the greatest musical result, but it was certainly interesting to see what would happen. So yeah, in conclusion, I think it's been really fun getting here. I have a few thoughts on the technology as well. Since this is kind of more of a programmer-oriented environment, I can share some thoughts on kind of the programming part of it. Basically this is entirely programmed mostly from scratch. I used a machine learning library for the handwriting recognition. Like I said, there's a bunch of these you can get, and I can give out links later on if anyone's interested. All of the graphics I made in OpenGL, the sound engine is basically something I made myself as well. Basically from scratch, just using kind of the basic processing callback from iOS. I don't necessarily know if I would recommend that approach, but one of the things that this did really help out with is, for things like drawing, you can get like hundreds of waveforms and be able to draw all of those dynamically. And I think that's a really important part of this, and a really important part of like the kind of sonic exploration that I want to enable. Is that you can see basically what each wave or what each processing node is doing to the resulting audio. And so like every step of the way you have this visual indicator of like, oh, okay, that's crazy, that's what FM looks like. You can see the wave basically compressing and expanding. So it's pretty cool to have that, and I don't know if that would be possible without basically the approach I use, which is like I have a shader where I just pass in a raw audio buffer, and it just basically spits out the pixels needed to draw that audio buffer. I think it would be a lot harder to do kind of the level of graphics that I wanted for this without basically going totally from scratch. Problem is, it takes a lot longer. This project has been going on for a while, and it's just harder to work with these tools. So it's always a trade-off of like, do you build the thing and get like the absolute maximum performance, which was certainly my mindset at the time. I don't know if I would make that same decision now, but the alternative is, do you use all this stuff that you get for free from a library, from a framework, and then maybe do you run into limits at a certain point, depending on what it is you want to do. So skipping back ahead, that's more or less most of what I had to talk about or what I had prepared today. But definitely, if you're interested, head to our website. Feel free to sign up for the mailing list or follow the social media accounts I have, either for Orglyph or my own personal account. Feel free to get in touch as well if you're interested about any of the work that I've done with Output. And thank you for having me.
Yeah, thanks, Spencer. I think we have a bunch of questions, don't we, Josh?
Yeah, loads. So one question is, can you folder a project within have a pod within a pod?
Yeah, that's a great question. I built that. It wasn't very stable, but that's sort of the idea, is like you would be able to kind of cascade these things, and also use that as like something for polyphony. There isn't really a great polyphony story. There is MIDI input. So like if you plug in a keyboard to this, you can you can get that information and map that to sound however you like. But imagine if you could like basically take an entire patch, circle it up, and then like copy it like 8 times, and you have like an instant synthesizer.
Yeah. Great. Expensive Brother asked a question. Can you talk a little bit about the approach of representing patch chords in code?
Yeah, it's it's a tricky problem in some ways, but there I did spend a lot of time with it, and the patch chords themselves, they display an audio waveform. That's kind of like probably one of the trickiest parts of it. One of the things I did do, I mentioned this, basically I wrote a custom OpenGL shader that draws the waveform given just a straight audio buffer. So you don't have to copy anything. You just take the audio buffer that you're passing between the 2 nodes that already exists. You give it to a shader. The shader does the rest of the work. So it's very low cost to actually draw the patch chords and all the the additional data. The other thing I'm doing there is I'm scaling them in a weird way. So what I'm doing is I'm basically estimating the gain of each patch cord or of each waveform, and doing, I'm basically normalizing it to kind of like a gain of 1. And then I rescale it according to the estimated gain, but logarithmically. So that way, basically, as your sound gets louder and louder, the visual representation doesn't occupy the entire screen. And it actually makes like a better sort of like visualization, because it also maps to the way that we hear sound. If you double the amplitude of a wave, it doesn't sound twice as loud. It sounds, you know, somewhat less than twice as loud. So I wanted to have a way to basically visually represent that as well. And then lastly, the connections between the control nodes are kind of totally different, and they're kind of more at a control rate basis. And like there's a fun bag of tricks that I had to use to get that all to kind of look cool, but similar sorts of ideas.
Great.
I do actually have a question myself as well. I'm really kind of curious about this whole graph stuff. It's like, first of all, like presumably underlying this graph, you have some kind of data structure for that you've written yourself, right?
Mm-hmm.
So there's kind of two ways of doing a graph like this. As far as I know, you can do like kind of like push or pull, right? So you can say, okay, so these are like the starting nodes, and then we have cables going to these other nodes, and you're gonna just kind of do it like a topological sort and treat that as a DAG and like go from input to output. Or you can do like the other way around. You can start by, this is what I'm outputting, and you know, what is feeding into this and what is feeding into this, and kind of go up instead. So which one of these are you using and why?
Yeah, it's a great question. This is just a pull. It's a pull architecture. So basically, you start at the output, and then you just kind of like go back, and every node keeps asking the nodes behind it for samples until basically everyone's processed the samples that they need to. I chose that direction mainly because that was what I was most familiar with. That's what Chuck uses. I will say that it's not the most efficient. And I think that's okay for this. It actually, like, efficiency has not been a problem. You know, like I was originally developing this on like a 2012 era iPad, and being able to get hundreds of nodes up and running. And so, you know, I think like you could make it more efficient by a bunch of different approaches, but basically pulling from nodes and like all those cache misses, like it's not great for audio, but it's been fine. And I think like that's always going to be my perspective on performance optimization, is like when you start to hear clicks and stuff, like things that users don't see that are a problem.
Yeah, I think that's really great advice as a kind of a general strategy. I can definitely get behind that. Thanks for explaining that.
Right.
For sure.
So there were a couple questions just around the future plans for this. Any plans to render it in 3D? Any plans for an iPhone release, or is this exclusive to iPad?
Yeah, that's a great question. Or those are great questions. I started to toy with the idea of doing like a version, because you know it's easy to think about this, and then you know you see something like you know, like a lot of the kind of cool VR apps that are similar to this, and like be like, let's go do it that way too. I think what I do like about this is it is a little bit more accessible, and I think like, you know, I approach these as sort of research problems where you sort of have to understand kind of the medium before you get really like, you know, really deep into it. So, you know, I wouldn't want to, you know, really kind of have a half-hearted effort into as far as like VR. But I can totally see that direction, and I think that also enables like a lot of other features with like collaboration and stuff like that, and as well as engaging space a little bit more. For the phone version, yeah, I think that's likely. You know, it is a little bit different just because it's just a smaller screen and it's a little bit harder to work with, and it does make a difference.
Great. And you said all the graphics are done in OpenGL. So there were a couple questions as well about architecture. So graphics were done in OpenGL. The processing engine is all done in raw C++. Is that right? Or was it done in Swift?
Yep. Raw C++. Yeah,
Oh.
it's C++ all the way,
Yeah.
which presents its own challenges. You know, it is very much like an object-oriented architecture. And basically, the rough idea is that every node kind of has a couple of different representations, which is its own kind of like complexity. But basically, there's kind of the audio representation. What does it sound like? As well as the graphical representation. What does it look like? How does it draw itself? And in some ways, these are related because I didn't really show this too much, but like a lot of the nodes, they appear differently depending on how you've configured them. And you know, I think that as well is like an interesting direction to go in. Like, you know, as you change your envelope, like you should see that envelope, you know, look like the way it actually sounds. Maybe even have some feedback as far as to like what part of the envelope it's in. And then, you know, with the graphics system, it's similar to the audio system. You know, it's like kind of like an object kind of entity-based model. So basically, everything that's drawn on screen has a class and a class instance associated with it. So nodes are their own kind of class, connections are their own kind of class. The patch cables, all the UI, you know, that's its own kind of class that renders itself. So that's kind of the basic model, and it's the same general concept. Basically, you have a list of objects, you just iterate through them all and draw them or render them until everything that has rendered has done its thing.
Great, thank you. Another question: can you create feedback loops? And if so, how does that work with the pool architecture?
Yeah, you can create feedback loops. It's not super optimized right now. So with the poll architecture, basically, if there isn't a delay in your feedback loop, it'll have an implicit delay of your buffer size. So what I'd like to basically eventually tackle is like a loop detection. It's not necessarily an easy problem, especially if you get into like crazy loops that people might want to do. But I would love to have like a better solution for that, because there are so many cool ideas that you can get from like having feedback, like building your own comb filters and putting like you know, other kinds of filters like within the feedback loop of like whatever sort of feedback system you're making, as well as whatever crazy ideas like I haven't thought of yet that maybe someone else out there has.
Okay, great. Here's a question. They think it might be a little bit too generalized, but can visual and graph-based programming ever be accessible? Question. Yeah, I'm not sure if I understand that one.
Maybe for someone who's visually impaired, for example, maybe that's what they mean.
Yeah.
Yeah, that's a great question. You know, I think it is a challenge. One of the directions I kind of got in, you know, I think a lot of this was kind of motivated by accessibility, not necessarily to people who might be vision impaired, but more to people who don't have computers but do have a mobile phone of some kind. I think we're finding more and more like this is like how people, you know, experience computers is through a phone or an iPad or something else, basically. And like this trend will, I think, only continue. So I think if you don't really have tools for this sort of level of creation, you know, like if I didn't have a computer growing up, I wouldn't be talking here now, you know, like, and if I didn't know how to program, if I didn't learn how to program that computer and like have access to like these kind of more like off the rails sorts of you know, computing experiences. And so I think that's ultimately what I want to give to people is like something that like kind of inspires them. But as far as like kind of vision impairness, one thing I did think of, or one thing actually React Table does, is it has actual physical tokens. And so if you combine that with maybe like a haptic interface, you could probably actually make something pretty interesting.
Okay, great. Just getting a question from my son, actually. He's
Oh, cool.
he's asked this question. I'm just trying to understand him. So I think what he's asking is, will there ever be an option to be able to do like procedural code in Orglyph? So be able to do any sort of scripting or anything like that.
Yeah, I've thought a lot about that. And even like thinking about how would you, there's a lot of scripting languages you can embed these days into, pretty much any application you're making. And what I really want to figure out is like, how do you kind of go both ways? Because I think a lot of these environments, like Max MSP, for instance, there's an object where you can write some JavaScript code in it. But I also want to like say like let's say you're coding, like how do you have like an entire Orglyph program and like assign that to a variable or something? And like this is your graph, and then like you can manipulate that procedurally. So basically have this sort of like bi-directional interaction between what you're doing that's node and graph based and what you're doing that's procedural based.
Nice. Great. I think we got all of them. Yeah, I think that's it. Yeah. Well, thank you very much, Spencer, for that. That was really awesome.
Yeah.
Thank
That
you.
was really inspiring. Yeah, thank you.
Yes. Yes. So I think we're rounding up. I don't know if Celine is still with us or if she's lingering in the background. I see her video is still on. But yes, just a very quick announcement before we head off. Be sure to join us every second Tuesday of the month. So we'll be back here. I don't have the date right in front of me, but the second Tuesday of every month, we are here with the Audio Programmer Meetup. And I'd like to extend a very big thank you to everybody that's joined us. Oh, Celine's back. Yes, I'd like to extend a thank you to everybody that's joined us tonight. I'm going to do a little crew shot here for Twitter tomorrow. So everybody smile. We can make this like a tradition.
Yeah, I think we've been doing them all the time, but I was like, sometimes when I would do them, I would like just wait until everyone kind of looks into the camera and then do like a shot. Well, like I think it's better to do it like this, where you actually ask everyone.
Yeah. Yeah. Thank you. Thank you. And once again, let's just plug ADC one more time. This is the last week to submit for ADC. To get to the ADC website to find out more about ADC, be sure to go to audio.dev. And anything else that you'd like to say, Celine, before we sign off?
Not really. I'm really happy to be back around you folks, and I'm looking forward to meeting a lot of you, hopefully at the conference. Thank you for having me today as a surprise guest.
Yeah.
Thank you, Celine. Yeah, and please don't forget to submit to the ADC, to submit a talk to ADC. You can still do until next Monday. And if you don't fancy submitting a conference talk, please consider submitting something to this very meetup, which you can do at
theaudioprogrammer.com/submit.
Exactly. So then we can have you every second Tuesday of the month.
Yeah. Great. Well, we'll sign off now, and I'll end this stream. Thank you very much for everybody that tuned in, and we will see you next month.
See you soon. Thank you, everyone. Bye.